says 7,500. I thought so too, but apparently there's a lot more students in this class.
What are we talking about?
Just grading exams. I teach 54.
Ah.
Big class.
Yes, I know.
But you're done.
Yeah, I got it done yesterday. We're using grades books and that. Over half the class got it completely right, so I could just like put like 2 buttons. An hour.
Did take all day yesterday.
I think it took like 6 hours total.
Okay. All right, let's get started. First of all, just a couple of administrative things. One is that I hope I will find out on Monday that we will remain in this room for the rest of the semester. The person who has the final say has been on vacation this week, but the schedules that are online for the rooms indicate that this one has actually less problem with conflicts than 540 Corey, so they're going to try to make that happen for us. The other thing is I have put out the second homework assignment. It's on Git, and there's a write-up for the assignment in the usual, homework/doc, homework2/doc. And the third thing is that now that I'm off the road for a while, I'm going to get together with Max and get the homework 1 graded this in a few days. All right. Any questions? So what we're going to talk about today is Fourier transforms, another algorithmic pattern, and really a beautiful one. This is, and in much the same way that numerical linear algebra has so much structure that you can really do a very good job of making it run fast. Discrete Fourier transforms have so much structure that you can do that as well, and we'll dive into that, probably not in this lecture so much, but sometime next week. So first of all, I'm going to review the math. Continuous Fourier transforms. Given a function on from 0, 1 to the reals, we can define its Fourier transform using this integral, and it's defined for k equals 0, plus minus 1, plus minus 2. It's a set of discrete wave numbers. And you can define the inverse, which is take the amplitudes of this, the f hat k's, and reconstruct the function again. So the way to think of this is that you're expanding some function is you're finding the expansion coefficients, the f hat k's, of a function as a linear superposition of trigonometric functions, essentially complex trigonometric functions. It's useful in a number of settings: approximation theory, solving PDEs, and signal processing. Frequencies are thinking in terms of things in wave number space is very productive. So here's some of the things you can get out of Fourier transforms. If f is a q plus 1 times differentiable periodic function, then you take the Fourier expansion and truncate it up to minus m to m terms. That's a finite truncation, and the error that you make, so if you take that function and compare it to the original function, the error is order 1 over m to the q, where q is how many derivatives you have. So, so if you have enough derivatives, you can get a very rapidly converging approximations as you increase n. So if you have 10 derivatives, every time you double the number of points, you decrease the error by 3 orders of magnitude. Second example is that if f is a smooth function, then df dx is just take the Fourier expansion and multiply each expansion coefficient by I times k, where k is the wave number. So the way to think of this is that if you think of the derivative as being an operator or matrix, then Fourier transforms diagonalize the derivative. So for dimensions greater than 1, we can apply 1D transforms in each direction separately. I've just written down what this is. So you're on a unit cube, d-dimensional cube, and you just compute the expansion coefficients for elements of integer tuples k0 to kd minus 1. And same estimates and derivatives from 1D apply to partial sums and to derivatives as well. So that's what the continuous Fourier transform is. What is the discrete Fourier transform? Given a set of discrete set of function values on an equally spaced grid, so you have fj, j goes from 0 to n minus 1, where fj is say equal to f of jh, where h is 1 over the number of points, and fn is equal to f of 0, so f is periodic. And for simplicity's sake, we're going to take n to be even. We can define a discrete Fourier transform, which is the sum of fn of k, f sub n applied to f for the kth discrete Fourier coefficient, is we're just replacing the integral that we had before with just sums, fj, e to the 2 pi I, k times j times h. So if you go back here and look at this integral, what you see is that we're just replacing this integral by a pretty simple quadrature rule. And you can, and for the particular range of k's, the kind of conventional range of k's is to take k goes from minus n over 2 plus 1 to n over 2. You have to have, so that's the standard way of defining discrete Fourier transforms. And and a really compact way of defining them is that if you define z is equal to e to the 2 pi I times h, then this is just 1 over n sum from j equals 0 to n minus 1 fj z conjugate to the kj. So it's just a very simple geometric looking series multiplied by f's. Another way to look at it is that we're taking the inner product of f with wk's, where the inner product is just the discrete inner product q inner product r is 1 over n sum j equals 0 to n minus 1 qj rj conjugate, discrete inner product on complexes, and wjk is z to the jk. So you can think of this as taking as doing an expansion in terms of wk's. Well, I have to justify that statement. We could have used any contiguous set of wave numbers. K goes from k0 to k0 plus n minus 1. But you have the same answer encoded in that. And the reason is that one way of looking at it is wk is equal to w of k plus n. And that's because z to the n is equal to 1. So there are lots of ways you can shift around your discrete expansions for convenience sake. And we will do that shortly. So I said that one way of looking at the discrete Fourier transform is that this is an expansion in terms of the WKs. Well, the justification for that is that the WKs form an orthonormal basis for the n-dimensional complex vector space. So you have the inner product of WK prime is the sum 1 over n, j equals 0 to n minus 1, z to the k minus k prime j. That is a geometric series. So it's equal to 1 if k is equal to k prime, and it's equal to 0 if k is not equal to k prime. End of story. So you have a complete orthonormal basis. The DFT, the discrete Fourier transform, is invertible, and you get fj back by just writing out what the expansion writing out what fj is in terms of expansion coefficients f inner product wk multiplied by wkj. So it's just writing out the expansion, and in fact, lo and behold, we get the inverse Fourier transform, discrete inverse Fourier transform out of this. So this is the discrete analog of a Fourier expansion of a function described earlier, and the inverse transform, which takes you from discrete, in this case where the points in real space are discrete points, it's discrete coming and going. They look very symmetric when you discretize. So discrete Fourier transforms have analogous properties to the continuous one. For example, if f is some q plus 1 times differentiable function evaluated at the grid points, if little fj is big F evaluated at grid points, where f is q times plus 1 times differentiable and periodic, then f minus fn of x, so you evaluate the, so what is fn of x? Fn of x is take the Fourier coefficients and multiply them by continuous Fourier modes. So it's a finite sum, k equal minus n over 2 to n over 2, of these continuous Fourier coefficients, of these Fourier coefficients that you computed using discrete Fourier transform, and then you multiply them by functions, by the complex exponentials. That approximation has the same kind of error behavior as the continuous version of that. That is that it's 1 over n to the q, where n is the number of terms that you've kept in your Fourier expansion, and q is how differentiable you have. How differentiable your original function was. Again, double the number of points, and q is equal to 10. Then you decrease the error by 3 orders of magnitude. So this is one version. You will often hear people refer to things as spectrally accurate. So this is what they are referring to, and the property of spectrally accurate is to contrast this with what you have in finite difference methods. That in a finite difference method, or anything like the finite difference method or finite element method, you will typically have something that looks like h to the q, where h is the mesh spacing and q is the order of accuracy of the method. But it doesn't, q is not what it's going to be, that's what you're going to get regardless of the smoothness of the function. For spectrally accurate methods, the smoother the function, the faster it converges. That's why they are, for a lot of problems, so desirable. So here's another analog for discrete Fourier transforms that we saw in the continuous case. In the continuous case, we said derivatives just look like multiplication by the wave number. For discrete Fourier transforms, it's the same thing, except that what takes the place of derivatives is the shift operator. So wk j plus 1 is just equal to zk times wkj. So shifting by 1 is the same as multiplying the Fourier coefficient by z to the k. Z to the k does not depend on j, so you're just multiplying that vector. So here's a second derivative approximation to, or a second difference approximation to the second derivative. And we use this fact up here, and what we get is that we can express this as lambda of k times the Fourier coefficient at k times e to the 2 times e to the jk. Where lambda at k is z to the k minus 2 plus z to the minus k over h squared. So that's not all that interesting, because it's pretty easy to compute this. Well, it becomes more interesting if you take note of the fact that if you find a basis in which you diagonalize a matrix, then you can find all kinds of functions of that matrix using that same representation very cheaply. So in particular, if I wanted to find L inverse of f, what I do is I take the diagonal terms, I expand in terms of the basis that diagonalizes L, and instead of multiplying by lambda, if I were applying L, to get L inverse, I multiply by 1 over lambda. So it's you now have a very cheap way, if you can get the Fourier expansions, discrete Fourier expansions, of computing inverses of constant coefficient operators. All this extends to multiple dimensions by applying it one dimension at a time. So if you're on a unit cube, you go through the same thing here. There's lots of notation here. I'll let you read it. The important thing is that you still have basis functions. They're basis vectors. They're basis vectors defined over your d-dimensional grid, but that's okay. And they're orthonormal. So, why is this? Why didn't this just take over the world, kind of at the beginning of computing? Well, here's the reason. A straightforward implementation of computing the expansion coefficients cost O of n squared operations. So here's the computation of the expansion coefficients. So here's the computation of the expansion. You compute f inner product wk to get each expansion coefficient, and there are n of them. The inner product of f and wk takes order n operations. Each of those inner products takes order n, multiplies and adds. And there are n of them. So if you again compare to the cost of evaluating the finite difference operator, where it's order the number of points, it's the number of points times 3 or 4 floating point operations. Here it's the number of points squared. That's catastrophically bad. So you wouldn't want to use that. Now, so one way of understanding, kind of putting this in a context, is that in general, when you compute, if you have a system of orthonormal vectors and you want to compute the expansion of them, you want to compute expansion coefficients, if you know nothing else about the orthonormal vectors, what it looks like is matrix multiplication of the input vector by a matrix whose rows are the orthonormal vectors. So it's matrix multiplication. That's order n squared, and that's kind of intrinsic. Furthermore, it's matrix multiplication by an orthogonal matrix, so that the inverse is equal to the transpose. So that looks like a deal breaker, except until it wasn't. So Cooley and Tukey in 1965 first published the fast Fourier transform, and it's a wonderful, elegant observation, so elegant that people started going back and looking at history and found that the observation had been made by Gauss. If you look in Wikipedia, there's a discussion of some of the historical things. Gauss wasn't so much concerned about whether he could do this for large n in asymptotic time. He was just looking for a way to to organize the calculation so it would be less onerous. A calculation he was doing that used discrete Fourier transforms. Plus the paper that he wrote on this was not published till after he died, and it was written in Latin. So not a way to get it to be well known. So anyway, here's the basic observation. So again, we're assuming n is even. So we want to compute Fn of Fk, the kth Fourier coefficient. And that's the sum from j equals 0 to n minus 1 of Fj z to the jk. And now I'm going to shift the origin of k to be 0 to n minus 1. I said I could do that because I can always shift it back. And in fact, I tell you right down here how to shift it back. So now this is a nice series, but I can break it into two pieces. So j equals 0 to n over 2 minus 1 of f of 2j z to the 2jk, and z to the k times j equals 0 to n over 2 minus 1 of f of 2j plus 1 z to the 2jk. So what is this? This thing here, this first thing, is the Fourier coefficients of an input of half the size, and that input is every other point, is the data at every other point, all the even indexed points. This second term is an input of half the size, and the inputs are every other point but odd indexed. So this allows us to compute Fn of k one more observation. So this only makes sense if you're thinking in terms of, well, I have a box that does Fourier transforms on any length thing. This really only makes sense for some bounded set of k, but as I said, you can get all other k's by multiplying by 1, essentially. So here we have, so we can, if we know the Fourier transform on the even points, half the size, and on the odd points, half the size, the cost of getting the Fourier transform on all the points is going to be, well, for each Fourier mode, it's going to be input this, which you assume you know how to compute, input this, you know how to compute, do a complex multiply and a complex add. So that looks like order n number of floating point operations. The thing is that, let's say n is a power of 2. You can apply the same idea to these guys and keep going down, and thereby get an order n log n calculation. So here's everything expressed symbolically, because there's more structure to this than just divide and conquer. Is that Fn of the kth Fourier coefficient for a sequence of length n is the kth Fourier coefficient for a sequence of length n over 2, which are the even inputs, or the even indexed inputs, and then z sub n to the k times the kth Fourier coefficient n over 2 of the odd inputs. Now that just gets you up to k goes from 0 to n over 2, and then to get the last part you have to use the exponential, you have to use the fact that you can shift anywhere you want, and at the end, when the dust settles, you have, to get the odd ones, or to get the high ones, it's k at n plus 2, k plus n over 2, is, again, the even guys, the same ones we computed up here, and the odd guys, the same ones we computed up here, and the same coefficient that we computed up here, except instead of adding them, we subtract them. So it's a very simple algorithm. It has a very characteristic data movement pattern. It looks like things are, even though in principle you would have things talking to everything else, it's actually, you only have a very limited amount of data communication here. For a given k, it's going to be easy to see, and you'll see it, that you use for the k's for the n over 2 guys, you will use these values exactly twice, just for this one and for that one. So it's a very compact data movement, at least in one respect. So you can apply this recursively. Apply it so if we have n is a power of 2, until you get down to n to the n-1 sets of f2. How much does this cost? Well, at each level, it costs it costs one complex multiply, because this guy here, you're going to pre-compute that and store it. So it's just one complex multiply here. This complex multiply is used twice. It's used here, it's used here. So it's only one complex multiply, and then two complex adds. This one here and this one here. Times n over 2, which is the number of times you're doing this to get the n factors. So the total number of flops is, oh, and how much does a complex multiply cost? So I've written it out down here. It's a plus I times b, c plus I times b. You see 1, 2, 3, 4 multiplies, and 1, 2 adds. This add here is not really there. All that, in doing complex arithmetic, when you add a real and complex number, what you're just saying is that they go into different slots in complex. The real parts are all taken care of in one slot. The imaginary parts are all taken care of in another slot. Multiplying by I is a data movement operation. It is not a floating point operation. So where does this take us? How would we use this to, and as I said, so you do this at each level. You have a factor of 2 grid. You can keep going down. And then the total number of flops is the number of levels, which if your grid is 2 to the m, it's m levels times the amount of work you're doing at each level. And the amount of work you're doing at each level, it turns out, is the same. It's it's exactly 5n log base 2 of n, where that's the number of floating point operations, or 5n. And then the log base 2 of n is the m, the number of levels. So this leads to an implementation like this that uses recursion. So let's say I wanted to build an FFT class, and here's a way of implementing apply FFT. So I take a vector of complexes as what's going to be my output, and a const vector of complexes that are going to be my inputs, and then something that tracks what level I'm on. So if level is greater than 1, then I construct the even and odd guys, and then set up the storage for the Fourier expansions for the even and odd guys. So I'm doing lots of copying here and setting up vectors. This does not look very efficient. It's still order n log n, but it looks messy. And then I apply FFT. I call this function again, but with inputs that are half the size, and with the level, which is keeping track of how far down I've gone, decremented by 1. So, and then I have a loop that computes f hat even times z hat k times f hat odd, z to the k times f hat odd. I suppress that. That's just arithmetic. Now, if level is equal to 1, then I'm down to the 2 by 2 case. And the 2 by 2 case is really easy. It's the same formula, but you can actually write out what the formula is. It's f of 0 plus f of 1, f of 0 minus f of 1. That gives you the even and odd. So for a 2 case, the even is the 0th coefficient, the odd is the 1 coefficient, and z to the k is equal to minus 1. Now, there's a bit of magic here, which we have not yet dived into formally in this course, which is, what does it mean for a function to call itself? What does it mean for a member function of a class to call itself? I'm going to let that hang for the time being and just assure you that it does something something sensible. We'll discuss that next time. That's right. That's right. It calls it. This is a, and that's one of the subtleties here. Is that if this were just a function, there'd be no ambiguity. Yeah, well, there'd be less ambiguity. You were calling itself, and there's a question of does it kind of start out with the same, with a new copy of all the state and things like that. Now, for a member function, it's calling itself, but it's calling itself relative to the member data of that class. And it is possible that that when you access that member function at lower levels, it could modify the member data of that class. It turns out you don't here, but you have to actually know that that's not, you have to know that that's going to happen or not happen, depending on what you're doing. As I said, recursion is subtle when it's member functions, but the syntax is unambiguous. I mean, this is do whatever this function is using the member data of this, the context in which it does it is the member data for this object that is the instance that is calling apply FFT. And the apply FFT the default in classes, when you call a function inside a class, formally, you're calling a member function inside a class. Formally, you're saying star this dot member function. So this guy here, apply FFT, that means call the member function apply FFT to the current instance of the object. So star this is my current instance. One more piece of business that we have to deal with is what about complex numbers? One of the things about kind of C++ was that there are certain things it was oddly stubborn about, and C too, C as well. And one of them was providing some sort of minimal support for scientists. Complex numbers are a relatively late addition as a first-class object, and even then they're not quite as first class. They're members of the STL. They're members of. They're not really primitive object data. They're an STL class, and what are they templated on? Well, they're templated on the type of the real and imaginary parts. So you can have complex floats, complex doubles, complex ints, various kinds. Complex number is stored as a pair, real part, imaginary part, in contiguous memory locations. If you have an array of them, it's real, imaginary in contiguous memory locations. So how do you get access to them? You include complex, and I'm using the standard namespace as default. So complex of int, this is what the constructor looks like. That will give you an int of whose entries are complex int, whose real and imaginary parts are 1 and 2. And you can then square that using complex arithmetic. Makes perfectly good sense. Complex float, C of 1 point, 2 point, and then you can square that using complex arithmetic. All of this just comes with complex. So imagine our relief. We no longer have to worry about writing our own complex data type. So let's go back and look a little more closely at what's going on in the fast Fourier transform in Cooley-Tukey for the case where we have a power of 2. So let's drill down. So we said, okay, we're going to call f at n over 2 on the evens and odds. What does that mean? If we're doing this recursively, f of n over 2 on the evens is f of n over 2 on the evens of the evens. That is, so it's going to be every fourth starting at 0 times z to the k of f of n over 4 on the odd of the evens, which is going to be every fourth starting at 1. Starting at 1 or starting at 2? No, starting at 2. Every fourth starting at 2. This guy here, it's the same thing because it's just pluses and minuses. F at n over 2 odd is going to be, this is going to be every fourth starting at 1. And this is every fourth starting at 3. And then similarly here. We can keep going and probe how many times we're calling this and what are they calling it on. So So now we go down to, we've now called recursively twice. So to do the n, to compute the n over 4 FFTs on the even squared on things that are every fourth starting at 0, what are we using? Well, we're using, let's see, how does it go? Is it every eighth? I think it's no. So it's. I'm sorry. It's. I think I have an off by one error. I suspect that this is. So if it is, let's go back here. So this is even. So that's going to be every other one is even. Even of even. Yeah, that's every fourth one. And then even is every eighth one starting at 0, and then odd even is every eighth one starting at 4, and then you continue on this way. So essentially, if you look at this closely, first of all, in kind of expanding the recursive calls, you're getting more and more calls as you get deeper on shorter and shorter data. How good or bad that is, not clear. But the other thing that's happening is that it's acting on kind of very orderly chunks of data, but they're not orderly in space. They're orderly in wave number space. That is, it's every fourth or every eighth element of the data. So, and that's in a very orderly way as you go down deeper and deeper into the recursive hierarchy. So here's a way of thinking about this, and you can actually write a Cooley-Tukey implementation for powers of 2 that look like this. So you get down to the bottom, or a bottom. So I'm doing an FFT of length 8. And what are you going to do? So you're going to do pairs, and it's going to be every fourth starting at 0. And what that will do is update these guys here. You will get 0, 0, 0 will change 0, 1, 0, 0 will change 1, and then the inputs for this guy here are going to be this guy and this guy. The inputs for this guy here are this guy and this guy. Now, and you do that for every one of these, and you get a bunch of pairs that have been updated. Now, the way to think of this is that in the as you come up the recursive stack, you're going to be working on this chunk and this chunk separately. So you're going. This is now you've done 2s. Now you're going to work on chunks of size 4, and what's that going to look like? Well, so it's all the things have different colors here are one chunk, and then it's the same pattern for the second chunk with those different colors. So what's it going to look like? Okay, to get this guy here and this guy here, it's all evens and even, odd, even. And you use this pair to update this guy, and you use this pair to update this guy. So you get zeros, you get the reds and the blues updated at the next level in the recursion. Similarly, this is the data motion, and on the other side, you have a very similar data motion. Now you're getting more localization here. You're now looking at shorter strides, but also smaller chunks. Now finally, to do the final step in the recursion, as you're coming back up, 0, 0, 0 and 0, 1, 1 come together to get 0, 0, 0 and 0, 1, 1. Similarly all the way across, and then you get your full FFT. So how do we take advantage of this in a real implementation? Let's change the order in which we store the function values in memory based on reversing the order of the binary digits. So if we say, let's take a new vector, make a new vector j, and the way you construct that new vector is you take f, take that original, so take this j, expand it in binary, and reverse the order of the digits. That will take you from that will put things that have the least frequent changes into things that have the most frequent changes. So if you do that, here are the values for the reversed order digits for the case we have 8, 0, 4, 2, 6, 1, 5, 3, 7. Here is the original ordering, and here's the reversed ordering, 0, 0, 0, 1, 0, 0. It's a different order, and it corresponds to this in decimal. Now, how does our algorithm look? Well, now our algorithm has a lot better locality because these guys pair together and do the reds. These guys pair together, do the blacks, pinks, blues. Now these 4 group together and do compute all the reds. These 4 group together, compute all the blues, and then you do everything all together. Furthermore, one of the nice things about this is that there's you can do this without recursion. You can do this, if you do this initial sort, it's really easy to do this as a loop. And it's entirely update in place with a pair of complex numbers as temporaries. You know, how is this going to perform? It looks like you're doing less function calls. It looks like you have more locality, except at the beginning you've done something, you know, you've had to do the shuffling. Okay. So that's another way of getting some sense of how the data pattern is. Now, what I want to do is show you something else, which is, don't worry about the algebra here. I spent a better part of an hour on the plane back from DC last night getting it right, so I'm reasonably certain of that. But in fact, there's going to be a picture next that will tell you what the algebra tells you. But let me just, to justify that hour, try to walk you through a little bit. So this is the split radix formulation of FFTs, and there's a very nice paper, review paper from 1990. That's at this point the standard reference for this by Duhamel and Vetterli, Fast Fourier Transforms, a tutorial review and state of the art. And that's kind of the go-to reference for certainly for a lot of people, including me. So let's say you want to compute an FFT of size n, where n is just a product of two integers, n1 times n2. So here's a fact, and it's not hard to guess this fact, given what we've seen, is that you can express the FFT as a composition of 2 sets of FFTs, one of length n1, the other, one set of FFTs of length n1, the other set of FFTs of length n2, and then you have to put some multiplications in between them. So I will walk you through the beginning of this, just the first line. So this is f hat of k2 plus n2 times k1. So what that's telling us is that we're going to get contiguous indices in wave number space for the 2's and stride n2 wave number access for the 1's. So this is, all I'm doing is taking the original FFT sum and breaking it into 2 sums. That's perfectly okay. And the important thing here is look at this exponential. If you look at this exponential, what you find is that you can break out Zn J2 n1 times k. Well, the important thing is that Zn, which is the nth root of unity, raised to the nth power, since n1 and n2 are products, are the product, the n1 times n2 is equal to n, that's the n2 root of unity. And when you do that, and you do a slight bit of rearranging, let's see, get down here, I guess you'll see it, is that you get f of J2n1 plus J1, Z n2 J2 K2. This is a discrete Fourier transform of length n2. And then you have some funny sum that doesn't look like a discrete Fourier transform at all, over from J1 is going to 0 to n1. and because the n is wrong and the j1s are wrong, the k's are wrong. But then a little more work and you get this. And let me show you a picture of what this is. So again, so if you have n2 equal to 4 and n1 equal to 2, what are you doing? You're saying, okay, I'm going to take all of the even points and do a discrete Fourier transform of length 4. I'll take all the odd points and do a discrete Fourier transform of length 4 on them. I output those, and then I do this multiplication by an intermediate. The term of art here is twiddle factors. So these are you multiply each intermediate Fourier amplitude by a complex number. Again, they can be pre-stored. And now you take the output of that, and you shuffle them into discrete Fourier transforms of length 2, and then that's it. So why is this better than our recursive form? Well, we've now kind of made the kind of outside and the inside symmetric. That is, we've broken our FFT up into two FFTs. One is a perfectly sensible self-contained FFT of one length. The other is a perfectly sensible set of FFTs of two lengths, of a second length. And then we have something in between. So now then, if we want to try to find a really good way of doing this, we can then look at each of those separately and how to split those numbers up. In the power of 2 formulation, you're kind of stuck. You have to do things one way or another recursively down to 0. So this is a much better way of doing performance engineering. It also exposes structure better. So by the way, just for completeness, this was n2 equal 2, n1 equal 4. But this is the real, this bottom picture here, this is for n2 equal 5, n1 equal 3. This really gives away everything about the split radix formulation. So if you ignore the algebra and just say this is ground truth, it tells you much of what you need to know. So let's say we have stored our input data as a matrix of n1 rows and n2 columns. And furthermore, we store it in column major order. That is 0, 1, 2, 3, 4, 5, 6, 7, 8 this way. Then here is what, so we're doing that, and if you apply the split radix algorithm, here's what it looks like, is that you sample in the along rows. So you're taking a row and applying a length 5 DFT to it for each of the rows. Now, what that's exposing is that to do this DFT of length 5, this is where you're doing data access that has non-unit stride. And the stride is the size of the other radix. So it's data access of stride 3. And you do that 3 times. And you do data access of stride 3, you store it in these slabs. Let's assume that you just updated in place each one of these rows, and it has the same data layout. Now you take and you multiply by your twiddle factors, easily done. And now the other FFT is to do the length 3 FFTs where you're doing unit stride access. And if you go back and look at the algebra, you'll see that's exactly what's going on. So you have x0, so you have these intermediate values that are stored along each column in contiguous storage, and then you apply a length 3 FFT, and you do it 5 times. So this has the right kind of cost structure. The cost of doing this is 5 times the, so it's 5 times the cost of doing the length 3 FFTs plus 3 times the cost of doing the length 5 FFTs. If you work at that a little bit, you'll get something, if you apply recursively to the power of 2 case, you'll get something that's order n log n. Now, there's one more thing here. What would happen if I pulled out that W in the middle, if I just didn't do anything, well, what I would have is not a one-dimensional FFT, but I'd actually have the 2D FFT for a matrix, for an array of 5 by 3. So in that formulation, in that world, what are the performance drivers? Well, you know, when we talked about cache-based systems, we said data access is a big performance driver. So the N2 transform accesses data with stride N1. The N1 transform accesses data with stride 1. That's stride 1 for complex, which is stride 2 for real. So that's you know, you have to balance the cost of data access with the cost of strided data access with the cost of the amount of floating point you're doing. As I said, you could have applied recursion on both sides. You could have had a split radix for the N2, a split radix for the N1, not for 5 and 3, but for larger radices. How deeply do you apply recursion? And then the third thing is that if the transforms are small enough, it may cost less to apply matrix multiplication form of the DFT. So here's a couple of examples that are indicative. And when we talk about FFTW in a little more detail, if you look at the internals of FFTW, which are machine-generated code for small FFTs that are combined in various ways, what the code generation does is it tells you how many floating point operations this piece of code does. So I can find out from FFTW, okay, tell me how many floating point operations your length 8 FFT codelet does. And it turns out it's a lot less than 5n log n. So, and it continues to be a lot less, well into, much further along than you think. And here's some hints as to why. So first of all, if you look at a length 4 FFT, there are no multiplies here. Why? Because multiplying by 1 doesn't do anything, if you know it's 1. Multiplying by I doesn't do anything, because all it does is change what slot you're sending it into. Now, it isn't that there's no arithmetic, because you have to do the sum, but you don't have to do any multiplies. Here I did the matrix representation of the 8 by 8 of the FFT for length 8. Now, again, you will notice that a lot of the entries in that matrix are either 1 or I, plus or minus. So no multiplies there. Total amount of multiplies you have are 2 adds and 2 multiplies times 16. So these are the 16 non-unit. And the fact that I get 2 multiplies rather than 4 comes from the fact that square root of 2 over 2 and square root of 2 over 2, the real and complex parts of those numbers are the same. So it turns out it cuts in half the number of multiplies in doing complex multiplication. But you have to know, you have to program this in a way that you know that. And the only way to program this in a way that you know that is to, that anyone knows of right now, is to use machine-generated code. That you can tell, okay, here are the semantics of these things. Here are the things to look for to eliminate certain operations, and that's how FFTW is implemented. There is software out there written by real pros, and you definitely want to use it, and you will use it for the next assignment after the current one. So, questions about FFTs? So. So let me talk about one more application of discrete Fourier transforms and FFTs. And again, it's a beautiful idea that, when combined with other things, is turning out to be a powerful tool. It has historically, and we're finding new uses for it. So, this is how a way of using FFTs to evaluate discrete convolutions. So I want to compute G convolved with F. So what does that mean? So I have G is some array. I'll do all of this in 1D, but it all extends to multiple dimensions in an easy way. So it's for any point, this should be an I, not a J. For any point G convolved with F evaluated at I is the sum over from J over j and z of g of I minus j f of j. And you want to do it, typically you don't want to compute an infinite number of locations, but on a finite number of locations. You just want to do this for a set of locations 0 to n minus 1, n locations, contiguous locations. And we'll put one other constraint in here, is that you don't have an infinite amount of data, you have a finite amount of data. So f is going to be 0 unless L is also in an interval of length n. Now, I could have made the lengths different. It doesn't change the arguments. It just makes them a little more, makes the algebra a little more onerous. So it's more or less clear that if you put this constraint on where you want to evaluate your outputs, and this constraint on your inputs, that you're only going to have to, you're not going to ever compute an infinite sum. At some point, for a point in this interval, you're going to be so far away that f is going to be 0, the contributions to this sum. So you'll always be able to convert this to a finite sum. So here are the two observations. And here's a precise statement about how you convert it. One is that we can replace the infinite sum with a finite sum. For any b greater than n, the sum over the whole interval is the sum from I equal, or from, these should be j's, j equal minus b to n plus b of g of I minus j f of j. I will fix all the indexing problems and put the revised lecture out on the Git site. For I going from 0 to n minus 1. So this not only says that I can pick a finite interval, but it says how big that interval is going to be. And not surprisingly, it essentially is doubling the size of your problem. It's saying the interval is going to be the size of the region I want to evaluate on, plus the size of the region that, the size of the region that my input is supported on, plus the size of the region that I'm going to evaluate on, plus some ones running around here. So this is just saying, just making a quantitative version of the obvious qualitative argument that this is not an infinite sum, it's a finite sum. The important thing about the choice of b is that the b is the same b for all of the evaluation points I. So I found a b such that for all of these points, I can use that same b. Second observation is that, again, if I use this b, the same b that satisfies this, we can replace f and g in this expression here by their periodic extensions. So g convolved with f, these sums over this, is equal to, and these are all j's, g tilde convolved with f tilde for I goes from 0 to n minus 1. So this is tricky. The trickiness is, if I want to evaluate this convolution for just I from 0 to n minus 1, if I extend g and f to be periodic over the interval minus b to n plus b, then these two sums are the same. And I've just defined what it means to extend to be periodic. So again, this is qualitatively not surprising. If you're far enough, if you choose a big enough interval, it can't tell what's outside of it. It can't tell whether you're 0, you're periodic, whatever. I've just put a number to that interval, and it's more or less the same number as you use up here to chop it off in the first place. Now, however, now we're in business because I'm now taking the periodic convolution of two periodic arrays. And now I can diagonalize this using FFTs. Remember, FFTs are a basis. The discrete Fourier modes are a basis. So if I define Q hat of K is, I'm doing this little bit of song and dance to get rid of the minus B's. They're just annoying. Q hat of K is the sum J prime equals 0 to n plus 2B of Q tilde of J minus B Z of to the Kj prime. And then the inverse these are just the forward and inverse transform formulas from discrete Fourier transforms. then if I take this to be q hat, then what is G convolved with F? Well, it's the sum from J prime equal to 0, G tilde of I prime minus J prime. So the minus B's and the I's and the J's cancel, and F of J prime minus B. Now I go down here and I say, well, the G is a periodic function on the bigger interval, or periodic array on the bigger interval. I can replace it by the inverse transform of its forward transform. So G of I minus J is GK, Z to the minus I prime minus J prime of K, times F. Now, I now use the exponential property. I get Z to the minus I prime K, Z to the J prime K. So now this is the forward transform of F. And so now what do I have? And I'm missing a G here. So this now becomes, I'm missing a G hat here. So now this becomes G hat of K, F hat of K. Take the inverse transform of the product of the two forward transforms. So now I've converted something that on the face of it looked quite hard. It looked n squared-ish. It looks like matrix multiplication again. And I've now converted it to something that looks n log n, two forward transforms and inverse transform. Extends easily to any number of dimensions. Also, I was careful to say if B is larger than n, larger than or equal to n, B becomes a tuning parameter in this. So one of the things that we'll discuss later about how FFTs behave from a performance standpoint is how much you can recurse, how much you can make them into, make the radix for an FFT into a composite number, product of smaller integers. Well, there are things, so for example, let's say I wanted to do this on this convolution on something of, oh, I don't know. Let's say I took n to be 37. 37 is a prime number. It looks like, oh, that's not good. What's going to happen? Well, it doesn't really matter because I'm going to have I am beginning to have doubts about something here, so I may have to go back and fix this because that 2b doesn't look quite right. But I will go back and fix it tonight. But anyway, the larger point is that I can make, you know, it's not that b is equal to n. It's that b is greater than or equal to n. So if I were saying 37 is 37 times 2, I can make that into 37, so that would be 74. That wouldn't be much better. Well, I can make that into 75. All of a sudden, that's, you know, 5 times 5 times 3. That's a very composite number. So that's a tuning parameter in doing discrete convolution. So final comments on the mathematics. So this is so again, why is this useful? There are lots of problems in which you really want to compute this. So let's say you're doing a molecular simulation. So you're pushing molecules around, and what you're going to do to approximate the forces that are not near the molecule is to do a convolution, is to compute the two-body forces on a grid and then interpolate from the grid. That's kind of particle and cell method for molecular dynamics. And then you make it particle mesh to get the near field correct. Well, this now will become if you can take this and turn it into FFTs, that becomes a fast way to represent things. Then you have to ask the question how accurate it is. That's a different issue. So final comments on some of the mathematics. As I said, you need to transform back to centered and normalized form. And the way you do that is you know that you can always add in and it changes nothing. And that way you can find all the negative ones. Why do we want this? Well, it's a symmetry issue for real inputs. So let's say all of your f's were not just general complex numbers, but real numbers, doubles or floats. One of the properties you'd like this to have is that when you do a Fourier interpolation, that you would get a real interpolant. Well, you have to have this set of wave numbers to get that. And the reason is that f hat of 0 and f hat of n over 2 are real, and the Fourier modes for that are real. So those are fine. And then all the others match up in complex conjugate pairs. And that, if you kind of unwind the mathematics, that will guarantee that you will get real interpolants from real input data. But you have to have that. You have to have these things paired up in order to get that. Another point that I haven't discussed here are sine and cosine transforms. You can do these things not just with complex exponentials. These are particularly useful when solving PDEs, allow you to do Dirichlet or Neumann boundary conditions. In fact, you can build a sine and cosine transform method out of a complex FFT method. It's not the most efficient thing, but it will work. But again, this is something you want to leave to the pros. So any questions? Okay, so now I'm going to spend the next 15 minutes talking a little bit about implementation issues. So let's say I wanted to define an FFT1D class. What would it look like? So public interface would be a default constructor. And I wanted to do this now just for powers of 2. So that's what you're going to be doing. I'm not going to ask you to do anything else. The argument a sub m specifies what that power of 2 is. So you have a constructor. You have a member function that is the forward FFT from complex to complex. You have a member function that's the inverse FFT from complex to complex. And then you have access functions. Tell me what m is. Tell me what the number of points are. And then I have the only member data I have are m and n. Now, given that 1D class, I could build a perfectly okay multidimensional FFT class. Again, I'd input for cubic data, so to speak. So I'd input the power of 2 it was going to be in each direction. I'd have a forward FFT that would be a rectMD array of complex of doubles that would take f as an input and update it in place to give me the forward transform out, and an inverse FFT that would take f hat as an input and update in place to give me the inverse transform out, and then access functions. Now, what does this have as member data? I have m sub n, n sub n, and then I have a member data which is an object of type 1D FFT, because that's the way you do multidimensional FFTs. You apply the same 1D FFT over and over again to pencils of data. So here's what the forward complex to complex FFT would look like, is that you strip out 1D pencils in the right directions, you compute the FFT 1D forward, and then you store it back in. All the rest of this cruft is just getting set up to do that. Now, what's wrong with this picture? Well, one thing is that I've given you 2 ways of organizing a 1D FFT. Recursively, and BRI stands for bit reverse indexing, so reshuffling the data. Now, there's a third FFT that you're going to do for your assignment for this, which is to use a library version, FFTW, which is an open source industrial strength FFT. There are other FFTs out there that you might want to use. Intel has their math kernel library that has an FFT in it. And this is a typical pattern with FFTs, unfortunately, is that typically what you use that's the industrial strength thing is the 1D FFTs. And then your use cases for multidimensional FFTs are just problem dependent enough that you do that each application tends to write their own. So you'd like to be able to, and in this case, for pedagogical reasons, I'm going to want you to try all three of these things in kind of a uniform, a uniform environment, and not just use text editing. Now, in C and Fortran, it makes sense to hand around pointers to functions. That's what functions are. They're jump to another address. So that's a function call hands off control to an address, and addresses are fixed length, so call by value on addresses makes sense. So you can pass functions as just some funny kind of pointer, a particular kind of pointer, through function calls. Now, we want to make this type safe. Make sure function signatures conform. So you don't want to have just an opaque handle. You'd like the type system to at least check the things that this is made up of will actually do something sensible. So this leads to inheritance. This is an important concept in C++. You'll see it a lot, and there's a question of it overlaps a lot with what one does for what one can accomplish using templates, and the boundary keeps changing over time. So what is inheritance? Inheritance is that you have a base class, FFT1D, that defines the interface, that is, what the function signatures are. And then you're going to have derived classes, FFTW1D, FFT1D-BRI, FFT1D recursive, that provides implementations that conform to these signatures. So what does that look like? So let's take our original FFT1D class and ask, okay, how would the .h file change? So I'd have the same public interfaces, all the rest of this, except for two of my definitions. Forward FFT complex to complex, CC, now has a keyword in front of it, virtual. And similarly for inverse. So what does that virtual mean? Virtual denotes a member function that must be derived by the defined by the derived class, or may be redefined by the derived class, or may be defined by the derived class. However, if you have virtual equal to 0, that denotes a member function that must be defined by the derived class. So what does that look like? So what else would we have? So we'd have this thing here, and in some sense it's this interface that my FFT multidimensional would see. It would just see something that looks like, it turns out, a pointer to an FFT1D. And all it's using is that these functions are all defined and hopefully do what I expect them to do. So how do I define the implementation? Well, at the level of the header file, I have here's the concrete, the derived class derived from FFT1D. And what I tell it is that this is an FFT1D, and furthermore, the interface is public. So the FFT1D part of it is public. So what that means is that there is going to be all the functions that are already defined in FFT1D are defined for this. And then the two virtual ones that were equal to 0 and therefore not defined, I have to provide a definition. I provide a definition. That's what I'm telling the compiler here, is that you need to look, or the linker actually, you need to look for a function that looks like this, with this signature. I'm also doing something else here. FFT1D had a default constructor, and it had a concrete constructor, and I'm defining my own versions of that, even though there were default ones defined. So how does this change our multidimensional FFT example? So we have, instead of FFT, so we have a default constructor for MD, and now we have a constructor that says that takes as its argument an FFT1D pointer, a pointer to an FFT1D. So, and then it has forward, all the rest of the interface is the same. Now, why doesn't the constructor have M in there? That's something you should ask. Well, it turns out FFT1D has M encoded into it. That's part of its construction process. So I don't have to pass it in separately. Now, what does the data look like? Well, I have here a pointer to an FFT1D. So multidimensional FFT, this is all it's going to see. It's going to know I have an FFT1D pointer, and I will use it. Now, how does the solve change? How does the actual FFT multidimensional change? Is that instead of calling the member function forward FFTCC, I take the pointer and then do a dereference call. So this is how you call member functions of a pointer to a class. It's arrow. So that's all that changes from our original implementation. Now, there's still one more thing to go, is that I have to somehow get a version a version of FFT1D that's actually has everything implemented. How do I make that, and how do I hand that around? So here's how I make it, is that I am going to create a pointer to an FFT1D BRI, let's say. So that's a new, and then calls a constructor. Now here's the pointer to FFT. Now this is, I'm going to create also a pointer to an FFT, to the base class, and this is, take this pointer, so I know that FFT1D BRI is a FFT1D. That's how you refer to things that is derived from a class. So it's an is-a relationship. So FFT1D BRI is an FFT1D. So what I can do in particular for pointers to those things, I can say, okay, create a pointer that actually points to this object, the thing that this points to. But when I hand it around, it's as a pointer to an FFT1D. And now you call your constructor with that as your pointer argument. And what it points to is this implementation. But from the point of view of FFTMD, all it sees is that the interface is satisfied. The pointers to base class and derived task class are different types. And dynamic cast is a way of performing type conversion. So notice here that there's a template parameter to dynamic cast. It says what this pointer is being translated into or being cast into as a type. So why is this powerful? FFT1D can be used without recoding. So I don't have to change anything in FFTMD. Just use it. FFT1D defines an interface for the classes that interact with it. So this has a term that you should look up, programming by contract. The base class defines the contract that the object users expect to be able to call. You've already been doing programming by contract in your homeworks. Our header files have declared classes that you have been asked to define. Also, template parameters define a contract as a general rule. So what is the language of these contracts? So the virtual declaration says that your derived class can override this function. With equal to 0 says the derived class must provide an implementation because the base class doesn't have one. Classes with at least 1 equal to 0 are called pure virtual or abstract classes. You cannot build an FFT1D as defined here because there are two functions that are not defined. Compilers need everything to instantiate objects, compilers need everything defined. You can talk about pointers to abstract classes, but not pointers to things that have actually been constructed using new. We have an added member declaration keyword. Derived classes can see and manipulate public and protected data. Derived classes can't see private member data from the class that it's derived from. So templates versus inheritance. Both provide mechanisms for reuse. Templates, text editing and type checking, everything is done at compile time. Inheritance uses pointers, and that's always a bad sign. It's a mixture of compile time, checking function signatures, bases versus derived classes, and runtime, pointers defined at runtime. More general and powerful, inheritance can do lots of things that you can't really do with templates, although that border keeps evolving in time. So you can have derivation chains. You can have, if you think of the things of abstract algebra, you can have, you could have a class called group, and you can derive ring from that, which adds more things. You could derive division field from that, which adds more things, or a division ring from that, which adds more things. You can use derivation chains. You can also have multiple inheritance. You can have a class that actually has two interfaces from base classes. Now, when you do all these things, the interaction with the type system is subtle. So the conservative rule of thumb right now is that we use templates for containers and inheritance for function pointers and interfaces. Now, the final thing here, and I'm running out of time, so I'm just going to say, there is one thing about this that's really dangerous. The pattern that we had here, which is that, let me go back. I'll just show it to you where we did it. Yes. Notice here that we're creating a pointer with new, and we give it a name to hand it into FFTMD. The problem with that is that now who owns the pointer? Does FFTMD going to take responsibility for deleting it? Is that the responsibility of the thing that's calling it? That's really dangerous. When we had pointers that were pointers to data that were data members of classes, that was fine as long as new and delete were called in constructor and destructor, because then we could manage exactly who was responsible. Here, it's intrinsic to the way things work that the whole point of using derived classes is that the definition, the concrete instantiation of the base class, is coming from outside of the place you're using the interface class. So that puts in something that's just really something it's asking for trouble. And what I'll spend some time talking about next time is an STL tool, which is shared pointer, that makes that problem more or less go away. All right, so a couple of things, administrative things. I think we'll be here next week, but watch Piazza to make sure. Another administrative thing is I will be at office hours, but I'll be 15 minutes late. I'll be there about 3:15.